morning everybody. Welcome to the second class of this redox reactions, where we are so far discussing about the corresponding fate of two very important species. One is the water molecule and another is the dioxygen molecule. And since we are talking about the reactions which are either a reduction reaction or a oxidation reaction, and we have also seen in the previous class that utilization of photosystem 2, which is a typical natural process, and nature is responsible for utilization of water molecules for the production of the glucose with the elimination of this dioxygen molecule. And we definitely know there that whenever we produce some amount of this glucose molecule, at the end when we require this glucose as our source of energy, as our very survival, we utilize these glucose molecules for the synthesis of ATP molecules also. And these ATPs are our energy currency for all living system, including the human being. So, when the glucose oxidation is taking place for the production of carbon dioxide and water, we all know. So, these two reactions are very much interrelated in terms of electron transfer. So, these electron transfer reactions are that is why so important, and we should always know how this electron transfer is taking place. And related to that electron transfer reaction, we all know, starting from the electrode reactions, the electrode potential or the redox potential. So, we also know that something is also related to this as the different redox potential values. Then they are related to delta G0 values, then heat of reaction and all these. But the main driving force for all these reactions are the typical electron transfer reaction in a particular direction. So, if this electron transfer is going from the species, that means the species is losing electron, we call it oxidation, and when the species is accepting that electron, we call it a reduction. So, all these thermodynamic quantities and all these things, because we can find out these by doing experiments also, because knowing this chemistry phenomena is always related to the experiment, because we do the experiments and experiments will clarify some of these things. So, this electron transfer reaction, if we utilize it for water or the dioxygen, there will be heat transfer also, and the very basic thing what we know for these reactions is the corresponding energy which is released. So, some of these reactions are exothermic and at the other hand some of them are endothermic. So, the reaction will definitely tell that whether you have a situation where energy will be released or energy will be absorbed. So, if we just simply go back to this condition, that means that how this water is getting oxidized and how O2 can be reduced or O2 can be utilized for some other purpose, such as that simple combination reaction. Where we utilize this for attaching this O2 to some other species, such as A is attaching with O2 forming some cases AO or AO2, such as if A is carbon C, then we can have carbon monoxide and carbon dioxide formation. And at the same process, since the carbon is getting oxidized due to the formation of carbon monoxide and carbon dioxide, carbon can function as a very good reductant. So, in that particular reaction, we see that the carbon can function as a very good reducing agent, which can be utilized very nicely for the metallurgical processes that we will see afterwards. So, if we see that water can function as an oxidant. So, if water is there, which is a different proposition, that we know that water this particular thing that in the pH2, that is basically water is getting oxidized, but if we consider in a different fashion that how water can function as an oxidant. So, the transfer of reaction is of different type, and the reaction of water with the species A, say sodium, if it is sodium, is of different type, and in this particular reaction it is not that this will release dioxygen molecule from water, it is not the oxidation of water molecule, but it is the function of water as an oxidizing agent which will oxidize the sodium metal from Na to Na plus. And the fate of reaction is also twofold. One part is going as the producing hydroxide ion, the medium will be alkaline. As a result, what we see that if we consider that Na plus and OH minus attaching together and they are in aqueous solution. So, we get basically sodium hydroxide formation with the evolution of hydrogen. So, water serving as an oxidant will be releasing some amount of hydrogen from the water. So, hydrogen what is present in water, we know that from the typical ionic picture of water, that water is attached to one oxygen by 2 H plus. So, this H plus is always present in the water. So, in aqueous medium if it is there, so that H plus will be reduced and the electron transfer can take place from Na plus. So, Na plus will give that electron to H plus, producing hydrogen atom first, then the corresponding molecular form of the hydrogen, that means the dihydrogen will be forming. So, if we now consider two other things, that if we have the water molecule itself and if we consider in terms of the corresponding electron transfer potential, that oxidation of water, if we consider that simple oxidation of water what we find in the photosystem 2. So, that particular water will be utilized for the production of the dioxygen molecule through the formation of the OO bond. That OO bond was not present in the isolated water molecules. So, if we have that isolated water molecule present, so we must have at one position that we can establish some OO bond. So, electrons are being pushed to the molecular orbitals of this water molecule, and we have a large number of electrons producing in this fashion if they are giving H plus as well as electrons. So, these electrons are there. So, that particular electrons what we produce from these water molecules can be utilized for the reduction of this H plus formed over there, producing the hydrogen. So, for water we know that at pH 0 we know that the electrolysis of water all we know. So, at one electrode we know that we produce oxygen and another electrode we produce hydrogen, and this E0 values. So, this is the standard hydrogen electrode value which we consider as 0.00. So, if we set the scale at 0.00 volt versus normal hydrogen electrode, and with respect to that scale we just consider that others, that means the water, where the water is present for this particular reaction. So, depending upon that particular reaction what we find that where water stands against that of the hydrogen electrode. So, it is 1.23 volt versus NH2 which is quite high or quite above this particular scale. So, overall if we add up these two steps of reactions, one is the oxidation and another is the reduction. If we add up the overall reaction, what we get is 2H2O giving rise to 2H2 plus O2, and once we find out the E0 for the cell, definitely it is a cell reaction for electrochemical cell where we have the cathode and anode, and oxygen and hydrogen will be liberated in respective electrodes, and that particular liberation will give rise to a driving force for that particular cell reaction. So, E0 cell for that reaction is 1.23 volt by simple adding up of these two half cell reactions, and the delta 0 for this reaction, delta G 0 for this reaction is minus 475 kilojoule per mole. So, this is the basic or the standard scale where we just fix all these things and where we get these values for the corresponding transfer of all the different electrons. So, if we see that this particular thing is happening in a different way when sodium is directly reacting with water. So, sodium is functioning as a good species which will provide electron to the water. So, basically this water is very much close to the cathode, because we all know that the cathode is giving electrons. So, if it is the cathodic reaction is nothing but the liberation of hydrogen. So, this liberation of hydrogen will take place at cathode. So, at the cathode the reaction is this and your E 0 value is 0.00 volt versus NHE. So, this particular reaction, that means what about the E 0 value for the other reaction. So, this we know that the conversion of water to hydrogen. So, it is a particular half cell reaction. So, what about the other species which is reacting with the water molecule is the sodium metal. This is Na, and Na is transferring to Na plus, and he has a typical or natural tendency for producing this Na plus, and in that particular formation of this Na plus we get that a corresponding electrode potential for Na to Na plus. So, that is basically a typical oxidation process, and that oxidation process will have certain amount of values for our E 0 values. So, this particular thing is a completely different one. If we find this reaction, when we see that particular reaction when going for Na to Na plus, which is a typical oxidation reaction, and the electron is being supplied by the sodium metal. So, what about the nature of this particular transfer potential? So, the reaction of sodium which having a negative standard potential. So, all these alkali metal ions. So, immediately when we see that we have a negative standard potential for this particular reaction, we should always think about the corresponding positioning of this Na in the periodic table. So, in the periodic table it is in the group 1 element, where it is in the alkali metal, where we all know that the lithium, sodium, potassium, rubidium, cesiums are there. So, they will have some correlated reactivity pattern, where they immediately can go from Na to Na plus, K to K plus. So, these all alkali metals have a inherent tendency that it can react with the water molecule in a similar fashion, which will be able to release hydrogen from all these water molecules. So, this is one kind of reaction, and it is a typical example, a completely well known and well established example, a textbook example for water functioning as an oxidant. So, what about this functioning of this water as a reductant? That means what, when we talk about something, that how we have a typical species. So, one particular species we can have and that particular species in this particular discussion, it is the water molecule, and any other species will find in this universe that whether we will be able to take out electron one or more, or we give or inject some electron to this particular species. So, how much these all are stable? So, that is very much important in relation to the same species which we are considering as A. So, if A is losing that electron, A will be giving you A plus, and if A accepts one electron, we get A minus. So, what about these things? Basically, the availability of these species, the A which is in the 0 state or in the native state or in the elemental state, or its corresponding cationic version or this corresponding anionic version. So, that is very important. So, if this particular species what we get during the reaction of these, so whether this same water molecule can function as an oxidant or can function as a reductant. So, depending upon these particular reagents, so these are all we know that these are the reagents, or these reagents are the species which are functioning as an oxidant or reductant. So, all these things, that means related to all these our redox reactions, is that our oxidants and the reductants are the reagents. In a similar way or in a similar fashion, what we can consider that our electrodes, the cathode and the anode. So, those electrodes, cathodes and anodes can also function as an reagent, and in that particular case what we find that a chemistry which can be controlled by electron transfer coming completely from electrodes are known as the aspects of electrochemistry. So, in this particular case, if we just consider electrochemistry, we will be dealing with the electrodes. So, we can have the cathodes and the anodes, and what we can have that we can electrochemically oxidize this A to A plus, or electrochemically we can reduce A to A minus. But there are some reactions, and all the chemists always interested to know some chemical reagents. So, chemical reagents will be there what we can use for oxidizing or reducing a particular species such as A. So, there we will be utilizing the oxidants and reductants. These are all chemical species. So, some species which can be utilized for oxidation reaction, which can be utilized over here, and this basically will be responsible for the oxidation of A like that of our electrodes. Similarly, if we use reductant for this, and if this particular transformation, if it has a facile electron transfer potential, A will be going to A minus through the addition of the reductants or the reducing agents at this particular point. So, what about this water? So, we are talking here as that water will be using at a reductant. So, water itself will be reductant. So, some species will be there which can function as an oxidant during the reaction of this H2O. So, this textbook example for this water as an reductant is therefore, that we get here that this particular water as a reductant, where we get this as 2H2O plus 2F2 is 4F minus to 4H plus and O2. So, this is a typical example of oxidation of water molecule, where fluorine is the oxidizing agent. So, we all know that fluorine is the extreme right hand corner, upper right hand corner of the periodic table. It has the highest possible electronegativity, what we seen in my previous class. Now, we see that it is also functioning as a very good reducing agent, which can be able to oxidize the water molecule. How? Because this F2 has the highest possible electronegativity. So, it can very nicely accept the electron from the water molecule, because we know that the water molecule during some oxidation can give rise to a large number of electrons. So, these 4 electrons are coming out from 2 water molecules. So, these electrons, if they are attached to the fluorine atoms will be converted to the fluoride, and your oxygen will be liberated as typical dioxygen molecule which are derived from H2O, where H2O, this O is present as O2 minus. So, as typical ionic model, so what we get as O is present as O2 minus, which is the oxide ion. So, that will be losing 2 electrons. So, per water molecule we have to use or transfer these 2 electrons from this O2 minus, and that O2 minus will be giving you O0 or O only the oxygen atom, the nascent oxygen atom, and 2 nascent oxygen atoms forming over there, and that can be attached to another oxygen, giving rise to the dioxygen molecule for this. So, this particular point what we should be able to say that depending upon the corresponding tendency or the strength of the oxidizing agent and the reducing agent, we can have two different types of reactions on the same substrate. Your same substrate, that means the water as the substrate. So, water can be oxidized or water can be reduced, and we get different interesting reactions what we are just talking about, the corresponding formation of this oxygen molecule and the consumption of that oxygen molecule for the PS2, that means the photosystem 2, and the burning of the food material. So, if we just consider that a typical tendency that some of these reactions like that of our Na, sodium metal, that can also be true for alkaline earth metals such as magnesium. So, here is an example of this magnesium. So, magnesium we know that is a metal. So, we can have a metallic rod of magnesium, and that metallic rod, how it goes, because the metallic rod can be dipped in simple water molecule, and that can also be dipped inside a solution containing silver ions, that means the solution containing silver nitrate. So, what about this particular reaction? So, we are thinking something where we are trying to consider that the reaction of Mg with Ag plus. So, will there be any competition for this electron transfer reaction? That means, what we are looking for here is that Mg when reacts with Ag plus, that means the silver ion, the silver one, the silver ion, whether that silver ion can be able to oxidize this particular magnesium. So, silver ion will be the oxidizing agent or oxidant, which can accept the electron from the magnesium rod and itself can be reduced to silver 0, and magnesium will be oxidized to magnesium 2 plus. And the reaction stoichiometry will definitely tell us, because we have to balance the number of electron transfer from left to right during the reduction of silver plus, that means silver ion as 1 plus, we require 1 electron transfer, but for the oxidation of Mg we require transfer of 2 electrons. So, the stoichiometry would be 1:2. So, if we go from left to right, we see that some amount of magnesium will be coming into the solution. So, it is not that color, but there will be something, some color change can take place if there is some other metal ions which can give rise to a coloration by going to the solution. And silver, what is forming, where the electron transfer is taking place on the rod itself, because this is the contact point where magnesium rod is in contact with the silver ions. So, the silver ions will be deposited over here and some amount of magnesium rod will be decayed. So, this is the thing what we can think of in a different fashion, what we are discussing in our previous class, that how corrosion can take place, how rusting can take place on the iron. So, this is also of some type of that particular corrosion reaction, where some amount of magnesium rod is getting degraded, some amount of magnesium rod is corroded, but not in presence of only water and the atmospheric oxygen or moisture, but in presence of Ag plus. So, the metal ions which are present in these water molecules is also critical or crucial, because we all know that all water are not pure H2O. Suppose sometime we find that the industrial effluents, what is being discharged by industry, having several or large number of metal ions present in it, and sometimes we do not know what are the metal ions present in that particular industrial effluent. So, if something, some precious metal rod or metal pipe or metal strip or metal sheet is there in contact with that water environment which is bad, which has large number of metal ions including the silver ion or any other ion which is oxidizing. So, the rod in contact with that water which is not pure water at a particular pH. So, this can basically degrade this. So, it is another level of this particular corrosion reaction, where we find the rod will be degraded, because this rod will be leaching out, the magnesium rod will be leaching out as magnesium 2 plus, and if there is the possibility this particular ion will be directly deposited over there as the silver medal or the silver 0. Otherwise, it can form oxide in presence of oxygen or water molecule and will be degraded out from this and as form as a typical sediment over there. So, this thing, that means if we get instead of this particular thing, that means the oxide formation. So, what we have seen in our previous class, that rust what is forming is Fe2O3. So, this particular one, so this rust is basically forming from iron metal, and this iron metal which is not so high in that particular E0 values. So, this particular one will be weakly electropositive metal. So, if it is weakly electropositive metal, and it can give rise to the electron transfer reaction to give you ferrous and ultimately to the ferric, and these oxide ions which are producing from water molecule will give rise to this Fe2O3 which is our rust. So, that we have seen. So, in a similar way that we just say that these oxides which are having something where the weakly electropositive metal ions, they basically decompose also when heated to high enough temperatures. So, this is a different proposition of a different aspect what we are thinking, that now we have some oxide, and that if that oxide we heat it at high temperature, what will happen? Because here we are seeing that the metal is getting degraded by the formation of ions, by the formation of hydroxides or formation of the oxides. So, if we take some amount of oxide, because it has a direct correlation with the metallurgical process, where we find that the hydroxides will ultimately giving you hydrated oxides, and that hydrated oxides can be treated by some reducing agent to give you the metal back. So, this particular process is also very much interesting to know, that whether these oxides can decompose at high temperature. So, that is a very classic example of the decomposition of HgO, the mercuric oxide. In the inorganic chemistry laboratory classes also, we see that whether we have a sample of mercuric oxide, whether we can identify it by doing the reaction of this particular change, where if it is heated, it can be decomposed into the oxygen and the mercury metal itself. That means, the oxygen will be eliminated from the system. So, that is reverse reaction of that of our combustion reaction. So, combustion reaction is another kind of redox reaction. What we know, that any species or any metal which is A, which can be converted to AO or AO2. Similarly, any non-metal like carbon, if it can be oxidized to carbon monoxide and carbon dioxide. So, the reverse reaction of that is that if we take the oxide, any metallic oxide, any non-metallic oxide, any carbonate, any sulfate, whatever it is, if we go for or if we treat it at high temperature, what will be the fate of the system or what will be the fate of that particular compound, that we should always keep in mind. And when we are in this particular class of these redox reactions, we should always consider that whether some amount of electron transfer can take place. So, the heating of HgO is the simple heating of HgO itself, but if we use something where we have some reactive metal we can use. So, the reactive metal like zinc is used with that of your cupric oxide, and this particular cases what we state that the more reactive metal displaces the less reactive metal from its oxide also. So, in this particular case the more reactive metal is our zinc. So, the reactivity of zinc is higher than that of our copper in terms of the electron transfer reaction, but it is a simple, very simple observation, very simple reaction where we consider it as the removal of this oxide from copper to zinc. So, if we want to go for some reaction, that means a metallurgical process of any oxide, not that it is a copper oxide. So, any oxide if we can have, and if we want to get that particular metal from this particular oxide, that means the copper from copper oxide or cupric oxide. So, zinc metal strip, zinc powder, zinc granules can function as a very good reducing agent, which can reduce this particular cupric oxide to produce copper, and itself can go for zinc oxide. So, large number of reactivities we can find. Even in organic chemistry, we find the use of this zinc as a very good reducing agent. But here we are classifying this as a preliminary language, that is a typical displacement reaction, where oxygen is getting displaced, oxygen is being removed from copper side to the zinc side. So, if we consider three dimensionally the solid state structure of this copper oxide, which is a type of solid state structure of this cupric oxide. So, we will find that afterwards basically the structure will also be changed, because we will have a metallic structure of copper metal is itself, and zinc is going from zinc to zinc oxide structure, which has another type of solid state structure, which are the oxides of these metals. So, this particular reaction has a direct correlation with that extraction of some amount of elements. So, this reaction can be directly written for the extraction of copper from some copper ore. Suppose our copper ore is we are getting from the nature, from the earth crust as copper oxide. So, after enrichment, after purification, what we find that a certain level of concentration we can reach, and a very pure copper oxide can be in the final stage, can be reduced to copper metal, and this process can be considered as an extraction of copper from its copper mineral, which is copper oxide. So, this particular reaction, so always, because in this case the copper is present in the bivalent state, is a cupric state, that will be reduced to copper 0. So, extraction of these elements definitely also requires. So, metallurgy is also largely dependent on all these redox reactions. So, metallurgical processes are also dependent on redox chemistry, and the thermodynamics and the kinetics of that particular electron transfer reaction is also important, because we are considering something with appropriate potential values. So, we have to use a typical oxidizing agent or the reducing agent for this transfer. In this particular case, what we are using zinc for the reduction of cupric oxide is zinc as the reducing agent, but it should be appropriate one, because the potential is matching. Thermodynamically it should be matched for this particular reduction reaction. Otherwise, we can have some other metal, aluminum we can use, or some non-metal like carbon. Carbon reduction processes are also known for all this metallurgical extraction. So, what we find that in this particular case, that if we have some examples of these metallic and some non-metallic species, and if we consider that simple electron transfer reaction starting from a single electron to a triple electron transfer reaction, we see that by simply looking at the half cell reaction, because we are considering here, we are considering that we have the magnesium rod, which is having a potential of minus 2.36 volt, because this is the quantitative picture what we have seen so far from a reaction where we have seen that the magnesium rod, which is being dipped in a silver solution, silver nitrate solution or silver ion solution. So, this is the quantitative picture which we can get, that magnesium, when the rod is being dipped inside a silver ion solution. So, this particular magnesium rod will go into the reverse direction, because it has a potential of 2.36 volt in the reverse direction, and this particular silver ion will be reduced. So, silver ion will be reduced back to silver, because its potential is 0.80 volt only, and magnesium metal will be oxidized to magnesium 2 plus. So, in all these examples, so only few examples we have given, starting from the electron transfer potential values from the lithium, which is the strongest reducing agent of minus 3.05 volt to the strongest oxidizing agent, which is fluorine. So, that we have seen in our previous class by looking at the periodic table. Periodic table, this is the left hand side of the periodic table where it has electropositivity, and on the right hand side we have seen the corresponding electronegativity. That means the electronegativity is also high and it accepts the electron very easily. That is why this electron transfer potential is also very high for this reduction of fluorine to fluoride ions, which is 2.87 volt. That is why we have seen that the reaction of this F2 with water. So, if we just consider this water potential is not here, the E0 values for the water oxidation as well as reduction is not there, but we can have some rough idea or knowledge that what is the corresponding potential of this water for its oxidation and reduction. We can correlate how these non-metals and metals will also react with water in a different fashion, and also the different metal ions, how they react. If we just simply tabulate this, is a very simplified table where it gives with respect to the reduction of hydrogen, which is 0, we all know that is the standard reference for us as the normal hydrogen electrode. So, the reference normal hydrogen electrode we have, and with respect to that we have the upper side, that means the positive potential up to fluorine and the negative potential up to lithium. So, that also covers the presence of iron, presence of copper, presence of zinc and all these. So, we know that if we have a iron nail, we all know there is a common day practice and common day knowledge is that a iron nail, if it is deep inside the corresponding copper, like that of dipping magnesium inside the silver solution, though if this is iron, iron is just below this hydrogen electrode, that is minus 0.04 volt, and copper is just above this particular value of plus 0.34 volt. So, this particular value is well matched for dipping this iron rod to copper solution, a copper sulphate solution, which is copper 2 plus. So, this iron will go to this particular iron 3 plus, and some amount of copper will be deposited on that iron nail as copper, and you get the corresponding nail as the red brown nail covered with a very thin layer of copper. So, this is the typical driving thing, typical driving force which is associated for their inherent electron transfer behavior, because it is not a typical electrochemical cell what we are getting, but the electrochemical cell is formed when the rod is dipped inside the solution of the same solution of that particular metal, we get that. But this particular observation always we get. Similarly, if that particular copper rod is dipped into the silver solution, what will be the effect? So, all these values are typically important, and if we just little bit keep in our memory that what are the values for these and what is the typical trend, we can have some good idea about the corresponding reducing agent and the oxidizing agent related to the corresponding zinc, where zinc is there, because there are metallurgical processes where not only zinc, if we require more stronger reducing agent, which is aluminum, which is higher than that of our zinc. So, we require aluminum for that particular reduction reaction in the metallurgical processes, and sometimes we also use magnesium for that particular extraction of the metal from its ore. So, this is the thing that we are still with that particular rust. Now, we are moving slowly that particular rust to the corresponding mineral or ore. So, this is not F2, this is Fe2, sorry, this is Fe2O3. So, the reduction of this Fe2O3, what we are seeing that how we get that. So, this is the typical rusting process, and this rusting process we get this, we consider this as now as ore. So, one ore is Fe2O3, another one can be Fe3O4, that means the hematite and the magnetite. So, these oxides are there or the hydrated hydroxides are there, sometimes little bit carbonates are also attached to there, and this particular one, how you go for this particular one, that means the reduction reaction. So, this is the reduction. So, this reduction, if we use that carbon, we know that carbon is very good for the typical burning process or the combination reaction, C is attaching with O2 giving rise to our CO2. So, if this particular thing, that means this O can come from this oxygen of this rust or the mineral, that means the ore. So, this can be reduced back to this iron metal. So, this is a typical metallurgical process or the metallurgy. So, this metallurgical process will involve the corresponding choice of the reduction. So, carbon will be our reductant, which can be utilized for the reduction of this iron from its ore. So, iron we can produce in greater quantities than any other metal by reduction of Fe2O3, this is Fe2O3 with carbon or coke. So, that is the typical methodology we use for getting iron from its ore. So, carbon reduction is also feasible for other oxides. Say silicon, we know that the silicon, different silicates we know. So, if we have silicates like iron oxide, if we have phosphate as phosphate rocks, manganese, we also know that the manganese is present as MnO2 on the earth crust. This is the manganese dioxide, which is pyrolusite. So, that can also be reduced back to manganese metal by coke. Similarly, tin oxides. So, mostly all these oxides, we are talking about the removal of this oxygen by the utilization of a very fascinating reaction of carbon, which is coke, and that is the corresponding combination reaction of carbon with oxygen. So, this is the straightaway reaction. So, if we just take the same rust, whatever we are talking about, we are standing there simply that we have the rust in our hand, and rust is now our ore, that means Fe2O3 or Fe3O4, the stoichiometry is only different. So, which can be reduced by carbon giving rise to Fe and CO2. So, a part of this reaction, which is the formation of C2CO2, we can consider it as the formation of the C2CO2 as a typical example of combination reaction. In your books, it is written as a example of a combination reaction where C is attaching with O2 from the atmosphere or air, or O from your O3, giving a typical combination reaction. And these combination reactions are always very useful because carbon is getting oxidized. So, we are talking something which is comes under the purview of redox chemistry. So, C is getting oxidized to CO2. So, what about some more examples? So, magnesium we can use as the corresponding species for this combination reaction. As we have seen that magnesium we can use, the aluminum we can use. So, if our O2 is there, that means one reagent is our O2. So, this is the reagent which can be utilized for converting this Al, this magnesium to its corresponding oxidized form, that means Al2O3, MgO, etc. So, aluminum can be utilized like that of our carbon, what we can use for getting iron in blast furnace. So, aluminum can also be used for some reduction reaction of any oxide ore. Magnesium can also be utilized for this oxide reaction. So, another category of this combination reaction is that if we have the metal itself, and if we go the reaction not with oxygen, but another more electronegative elemental form of fluorine gas. So, what will form? So, we know that the barium is the electropositive element, and it is basically will be able to quickly remove the electrons from here, and it can immediately give you the corresponding salt of barium fluoride, like that of the thing what we have seen in our previous class as the formation of the corresponding salt of zinc as zinc iodide. So, this is therefore the barium thing. Similarly, this can also come for any organic compound. So, if we just correlate these, if we just think of all these things, and what about the corresponding combination reaction of CH4 or C6H12O6, what we are talking all the time, that the glucose oxidation reaction. So, the products are very simple in these two cases. Always we have carbon dioxide and water, because these are all made up of carbon and hydrogen, because these are all hydrocarbon type of thing or the sugar type of thing or the carbohydrates we have. So, carbon will take its own share of this to give you the carbon dioxide. Similarly, the hydrogen present in all these molecules will take its own share to give you the water molecules. So, this is a typical reaction where we get this combination reaction. What we find in case of this metallurgical process, that this particular reaction, if we just see that this particular reaction we have a corresponding free energy change, that means the delta G 0 value, the thermodynamically quantitative value for this is delta G 0 is a positive quantity. So, is not a thermodynamically very much feasible reaction, because we always know that the free energy change should be negative. The reaction will go very fast, is kinetically favorable as well as thermodynamically favorable. But this particular case, we see the reaction, we follow the reaction at room temperature. So, our room temperature is 25 degrees centigrade, and that room temperature is very useful to find out its corresponding delta G 0, which is plus 151 kilojoule per mole. So, the reaction is not at all a very good reaction, if at all it goes on the right hand side, because it is not thermodynamically feasible. Forget about its kinetic rate, because the rate of the reaction, how quickly, how fast we get, we generate this Fe from Fe2O3. So, what we do, we just simply see that their temperature, we just now control the corresponding temperature. If we rise the temperature of this reaction, so the reaction will be more feasible, and the contribution for this delta G 0, we know that from that T will be coming, temperature will be coming into the picture in relation to delta H and delta S, and that particular T will now control to drive this reaction towards a favorable condition, and we require a blast furnace, which is not 100, is above 1000 degrees centigrade, not 100, is above 1000 degrees centigrade. So, basically we see that like iron, so for highly electropositive metals like that of calcium, magnesium, aluminum, the oxides are too stable. In other case also, where we get that this particular one, that the electropositive metals like calcium, magnesium, aluminum, so delta G now is delta G 0 is too negative. So, this particular case also, that this is negative and is also stable, the required temperature would be also very high. So, we get that in a different condition we can have, and these different conditions can be formed for a particular reaction for this degradation from its corresponding oxides, or a reaction which is getting from the use of that carbon from that particular reaction. So, we can get therefore that this particular condition, then oxides of calcium, calcium oxide, aluminum oxide or magnesium oxide, from the metallurgical point of view, what we see that this can be extracted in molten condition, not in aqueous condition. So, molten alumina, and then we follow the corresponding electron transfer, not for any reducing agent, but is from the electrodes. So, the molten condition electrolysis will give the corresponding recovery of aluminum ion from alumina. Alumina is its ore. So, Al2O3 is its ore of alumina. So, alumina can be recovered from its molten condition. So, there also we require like blast furnace a high temperature, because we directly use this particular oxygen removal from our oxide ore. So, this particular reaction we go for a particular case where we see that a typical decomposition reaction So, if we consider that these oxides, so Fe2O3 is a reduction process, then other things are the corresponding decomposition reaction. One good example of decomposition reaction, because if there is no change in corresponding oxidation states of the cationic part or the anionic part, we simply see that when decomposition is taking place for calcium carbonate, we get calcium oxide and carbon dioxide, because this is a very good analytical technique also for getting estimation of calcium and its corresponding analytical values for presence of this calcium sample in any unknown material, because we can have this and we can be obtained from calcium oxalate also, because oxalate ions are very good ions which can bind nicely to these calcium centers. So, that can be oxidized to this calcium oxide and carbon dioxide. So, what about then this decomposition reaction, because we use this particular sodium hydride. In our previous class we are talking about something where we talk about that lithium aluminum hydride or sodium borohydride. So, these are the species, that means the thermal stability of these compounds are also important when we use for some transformation or reduction utilizing these, where it can supply the hydride ions. Similarly, the corresponding thermal stability of some compounds like boron, the boron diboron compound B2H6. So, if that particular one is not thermally stable, it can just simply go to the elemental boron and hydrogen gas itself. Similarly, so like that of your, this is another boron hydrogen compound, but these are all aluminum hydride and boron hydride compounds which we get from there as a hydride ion. Similarly, sodium hydride. So, this particular one where we have this as 1 plus sodium as the cationic form and this as the hydride. So, H plus. So, both of them can be moved to Na0 and H20. So, this is the typical decomposition reaction what we can follow nicely for sodium hydride also. And another interesting example of this is the corresponding decomposition of calcium chlorate, because these are the compounds where we can have one or more chlorine oxygen bonds. So, these are also very important in terms of the corresponding formation of this Cl2 with O2 in the chemistry of halogens or chemistry of these chlorides. But what about the redox chemistry or the redox reactions related to the formation of this ClO? So, the thermal decomposition of this will be simply the formation of the most stable one, that means the potassium chloride, and removal of this oxygen. Sometimes it is also very much explosive in nature, as this particular thing will remove some amount of oxygen directly from this particular chlorate. So, all these chlorates will be explosive in nature. So, this particular decomposition reaction also is valid for simple ammonium chloride. We all know that ammonium chloride we can form from the ammonia gas and hydrochloric acid or hydrochloric gas also HCl gas. So, this can be decomposed also by two things, that means your NH3 and HCl. So, this ammonium ion, which is also a very important, which has a typical level of oxidation which is -3 in an ammonium ion. So, this ammonium ion, if it is present along with nitrite or ammonium ion present with nitrate. So, these are very important in terms of the corresponding presence of these nitrate and the nitrite ions, which are oxidizing anions. So, the presence of nitrate or nitrite ions are oxidizing in nature, and the ammonium ion which can be oxidized nicely by the anion itself present over there in the salt. So, there is no need to supply some anion or some oxidizing agent from outside. So, the thermal stability of these compounds are also very less. So, they, if we allow them to hit it, so they will be producing something where we get this nitrogen. So, the nitrogen is in this nitrite is in +3, this nitrogen of this nitrite ion, and the nitrogen of this nitrate ion is +5 oxidation state. So, +3 and +5 oxidation state along with the presence of this ammonium ion in -3 oxidation state. So, that will be changed. So, is the typical example what we have seen, that you can have two oxidation states. So, one is A minus or one is A plus. So, similarly, if it is nitrogen, so nitrogen which is there, so nitrogen in -3 and nitrogen in +3. So, this A or N. So, this is nitrogen gas. So, it is in 0. So, always there is a tendency, always will have some tendency for these all these reactions is the typical electron transfer reactions. So, it will basically try to move to the lower oxidation state, and this state will also try to move to the lower oxidation state. So, the movement of these two species from +3 to -3 is the corresponding thing, which is very interesting, that if both of them are moving, when this is -3 and +3, both of them are moving, we get something where is we getting this nitrogen. So, N2, how we are getting N2? So, you see that is the interesting thing, that nitrogen from this part and nitrogen from that part. So, movement from this side and movement from that side will giving you N2, because we have to form a nitrogen triple bond over there, which was not present in this particular compound, because we have large number of NO bonds and large number of NH bonds. So, breaking of these NH and NO bonds are there by doing some very simple thermal reactions. So, these are basically simple thermal reactions. We can have some thermal analysis also. So, thermogram we can have to know the temperature at which particular point it is giving rise to the release of these things. But this is a typical nature of this decomposition reaction of ammonium nitrate, because the ammonium nitrate, where the nitrogen on the right hand side on the anion, which is in the higher oxidation state of +5, it will not be allowed to go down to N2 state, but it will have some interesting molecule like nitrogen in the lower oxidation state of +1. So, this will be +1 of nitrous oxide with 2 molecules of water. So, that is the thing, that how we get this particular one. So, when we go for the oxidation of this ammonium ion, which is present, so in some cases the decomposition reaction is such that the same ammonium ion in all these 3 examples what we see, which is very interesting, the presence of these anions. What are these anions are? These anions are Cl minus, this NO2 minus and NO3 minus. How good they are? Because this corresponding oxidizing ability or these oxidizing anions, this oxidizing ability is increasing. That is why we are getting these things, these different products. That means, ammonia we are getting in one case, nitrogen we are getting in another case, in another case we are getting N2O. So, in a similar fashion, if we can consider all other type of salts. So, one such salt is ammonium dichromate. The same philosophy we are considering. We are considering that ammonium is present and ammonium ion will be oxidized through this decomposition reaction, and this thermally how good they are, we have to just ignite it. We have to heat it or you have to ignite it. So, that is giving rise to some chemical volcano we all know, and this volcanic eruption for that particular reaction, the transformation of these things where we are going, that means the same ammonium ion. In all these cases we have the ammonium ions, and those ammonium ions are present, only we are changing from chloride to nitrite to nitrate to dichromate. So, this dichromate will be there. So, that particular dichromate decomposition also can take our reaction to the production of this N2, and along with this particular N2 we have Cr2O3 and water molecules. So, it resembles a volcanic eruption and producing basically sparks and large volume of green ash. So, this is forming as the corresponding green ash. So, this green ash is forming because some more amount of nitrogen gas is coming out from that particular ash. So, very loosely formed ash will be there, and the remaining thing what is there, which is basically the heap of this particular ammonium dichromate. So, we have this is particular part is burning. So, we have this particular green ash is there, because and you have this porous thing is also definitely is there, because the nitrogen will be coming out from that particular species. So, all this is about the corresponding decomposition reaction, and in our next class we will just start with some displacement and disproportionation reaction, and we will follow the remaining part of this class. Thank you very much.